Thanks everybody for being here. It's nice that you invited us and have us give a talk here. I have to correct Alexei on one thing. He said I'm the CTO of Apache Flink. That's not how Apache works. Actually, it doesn't have any CEOs or CTOs. Right? They're just like committers in the project and people in the project management committee. Okay. Yeah. So yeah, I'm here actually to give you an introduction into Apache Flink. Who of you has actually heard it before? Heard about Flink before tonight? It's a few hands at least. That's nice. Okay, cool. The talk is going to be a bit of an overview what the Flink project is about, and then I'd like to focus a little bit on the aspects on the streaming side. Yeah, let's just get started. Okay, so just to give you a little bit of background on Flink and the recent history. So it is within Apache a fairly young project, I would say. It's a little more than a year ago that it joined the Apache Incubator. It was still called Stratosphere. It's a project that came actually out of original university research. By the time we put it in Apache, we were not working for the university anymore. It was a few months old open source project on GitHub by then, and it was a fairly small stack back then, but with a strong inner component, a good runtime, which is a good foundation. And within over the last year, we've actually done quite a bit of work. So the community has actually the community has grown quite a bit beyond the core team, and managed to add quite a few components to this stack. So I'm actually zoom into that. What is Flink today? So when I say today, I'm referring to release 0.9, which is actually voted upon, I think, today. So if everybody likes it, it's going to be out by end of the week or so. So the most important thing about Flink, let's say the one thing you should remember if you go home and don't want to listen to anything else I'm going to say is it's actually a stream processor. The core is a streaming dataflow runtime that's streaming end to end, which presents itself as, well, yes, a stream processor and also as a batch processor, doing batch on top of streaming. It can be deployed in a couple of ways in different environments, and it has assembled a set of libraries on top of the two abstractions. We often refer to them as the dataset abstraction and the DataStream abstraction. Dataset being a finite set of data, a distributed set, and a DataStream being a continuous infinite stream. May also be a finite stream, but in general an infinite stream. Since we've been polishing the dataset abstraction a little longer, initially people were doing more batch than streaming, so we initially polished that a bit more. It has a few more libraries than the DataStream API, but this one's actually what we're focusing on a lot these days. So to give you just a very brief overview, I'm not going to talk about the libraries today in any detail. Just tell you a little bit what's there. On top of the data set, so for the batch use cases, there's compatibility wrapper for Hadoop, MapReduce functions, a table API, which is for relational style queries. It's something you can think of it as Link from Microsoft, where you write SQL, but not as a string, but as a sequence of like language embedded function invocations. Jelly is a library for graph processing. It's built on top of Flink's iteration and incremental iteration feature. ML, yep, you can probably guess that this means machine learning. It's also a library built on top of the iteration, incremental iteration feature. And then the gray components are not part of the core Flink project, but that are libraries that either we or other people have built on top of Flink. So there's integration with Zeppelin. It's also an Apache project for notebook, web-based notebooks. Cascading, a lot of you know cascading, I guess. This work in progress to connect this, to have cascading jobs run on Flink. Google Cloud Dataflow, the batch applications from Google Cloud Dataflow run, they can be mapped to the dataset API. And it's work in progress to actually have the streaming Cloud Dataflow programs mapped to the DataStream API. Yeah. Samoa is also a fairly interesting project. I think it's a project that came out of some people from Yahoo originally, and it's a library of machine learning algorithms that run on data streams. So continuous algorithms rather than algorithms on static data sets. So yeah, given that you have this abstraction and you have the stream processor in the middle, what does it look like if you actually execute something with Flink? So the dataset and DataStream API look like Fluent APIs in Java and Scala. These will, I think the syntax will look familiar. What happens when you start executing such a program in Flink? It's not going through the program lazily and really interpreting the data sets as in a way that, for example, Spark interprets RDDs. But what it does, it goes through it and builds a dataflow DAG. And in the process of building that, it sends it through two components called the type extraction and the optimizer. So it goes through, it does a lot of reflection. If you use Scala, we use also a lot of macros and generate a lot of implicit values to strongly type everything that goes through there. So it's building basically a schema in the background. It's pre-generating serializers and so on. The nice thing about this is when you write a Flink program, you basically don't have to worry, unless you're using very fancy types, about how you serialize them, right? It's using its own generated serializers in the background. They do fall back to cryo in some cases, but even then they look at what the types are that go through and pre-register them automatically. So unless you're using somewhere types that you load dynamically or that are not visible anywhere, this is typically something you don't have to worry about. For the programs against the dataset API, it also sends them through an optimizer, which is very similar to a database optimizer, only that it doesn't work on SQL queries, but on the relaxed operations that are in the Java and Scala API. As of the latest version, this is actually doing some interesting stuff. So it's running code analysis to the functions to determine some of the semantics, like how do input fields get copied into output fields and so on, because that's very interesting for the optimizer to discover potential. Okay, once this phase is done, what you have is a dataflow DAG. This is a horrible picture. Sorry for that. You can think about this really as a broad graph of vertices that are parameterized to do certain operations, and then have dataflow channels, logical channels that get bundled into physical channels with which they execute data. They exchange data, sorry. And this gets transferred to the master. The master checks this data structure and deploys individual operations, tells the operators how to do handshakes on the data streams and so on, what state each operator is in, and maintains the metadata for recovery. So let me quickly talk about a few use cases that we had in mind when we thought about how to build Flink, how to build the core architecture. So the four big use cases that we were initially thinking about is a low latency streaming data analysis, but also batch pipelines, machine learning and graph analysis. And we were looking what would be a common denominator for all these programs, or for all these applications to execute them efficiently and natively in a system, without actually working around in terms of trying to make, for example, I'm going to show you actually with a few counterexamples what we mean by non-native support. So the first one, what people have been doing a lot, and are to a large extent still doing today, is execute iteration actually just as a series of steps, a series of jobs. So if you run something in MapReduce, I think to a large extent that's actually also true in Spark. What you do is you have the loop, not really in what the master sees, but they're in the driver, right? So what you're doing is you're submitting a lot of jobs. In Hadoop, this was a big pain because the intermediate data was on distributed file systems. In Spark, that works much better because the intermediate data is in memory and it's referred to in memory, but it's still actually a sequence of jobs that you throw to the cluster. So the system isn't really aware that there's iteration. It can cache data, but it usually caches data as collections. It doesn't cache the optimal data structures in which they usually do the processing. I explained before that we have this optimizer step. So if you actually tell the system in a way that it understands deeply that this is a loop, it can actually do a lot of automatic optimization, figuring out what is loop invariant, caching that. It can, in the sense that, for example, SQL optimizers do push down of certain things, it can also try and push them out of the loop. So these are the sort of things that are interesting if you actually deeply embed iterations in a system. Another thing is stream processing. So if you think of stream processing, a continuous data flow is something that you would like to process as a continuous data flow. It seems a more natural abstraction. You can go the way and say we chunk this, we discretize this, we do mini batches. This is an approach that gives you a lot of that gives you a fast path to quite a fast approach to stream processing, but it ultimately hits a limit, because what you're doing is when you chunk this into streams, each computation actually looks at one part of the stream, and everything that is looking at more than one of these discretized mini batches is something that has to be aggregated across things that each of the mini batches computes. And you start working around a lot. You can make tooling that makes this appear more seamless, but it's ultimately not quite as natural and efficient usually as if you actually process the stream as a stream. So having those two examples in mind, and thinking about the common denominator of those use cases, the 5 corner points that we. I don't know what's going on with that switch. Okay, is that one on? Yeah. Okay, thank you. So the 5 design corner points for Flink that we came up with are actually, first of all, I said this in the beginning, really do everything on streams, right? The core engine should be a stream processor, completely pipelined, highly parameterizable, so the stream exchanges can be back pressured or buffered. A model that is pushing data but coordinating in a pull fashion. While this is nice, you can do everything on top of streaming. You can do batch on top of streaming, actually without a lot of complication. If you want to do it really efficiently, you ultimately want to add some special code paths for batch. These are not really a different code path in the execution engine in the sense that there are like 2 execution engines in Flink. It's more specialized scheduling modes for batch, or specialized recovery logic that can make the additional assumption that the stream is not infinite, so we can actually replay it entirely from the beginning, because it is a finite data set that we're looking at. I hinted at this before. We've added an abstraction that actually embeds iterations in the data flow, so the data flow is not acyclic. Not entirely. There's a restricted form of feedback you can do. The feedback can be coordinated across the parallel instances in a fashion that it bulk synchronously feeds back data. It can also be asynchronous in the streaming API. The 4th one may sound a little surprising. Why do you want to deal with mutable state in parallelizable computations? But it is actually one, if you support it, you don't need to expose it to the user, but at least if the runtime thinks about it in some terms, you can gain a lot of efficiency and flexibility. And the 5th one is basically an artifact of Flink being implemented in Java. And if you do extremely data-heavy processing in the JVM, you have to worry about how to deal with the JVM memory. And I think most projects have either done this or are heavily moving in this direction. I think Spark has started this with Tungsten now. I think Drill is extremely heavily engineered in that direction. And yeah, Flink also from the beginning has had this as a core design point. Okay, so out of the 4 use cases for Flink, I'd like to focus a little bit on stream processing here. So where to put Flink in the architecture of a streaming infrastructure? So if this is like a simplified blueprint of what a lot of people are doing in a streaming infrastructure in their company, you often have these 3 coarse-grained parts. The first one is the creation of the streams by various libraries, coming from taking server logs and shipping them or subscribing to database transaction logs. The part in the middle, the broker, this is where the Kafka project is very prominent, is buffering these streams, is dealing with making them available to multiple consumers, long-term storage. And the third part is doing actually something with the streams, figuring out what is happening, looking for event patterns, just refining them, enriching them, feeding them back in the broker, making a refined stream available for downstream consumption. And this is the part where Flink plays well. So what is special about Flink as a stream processor? What is different than, for example, Storm or Spark streaming? So I would say that Flink has a neat combination of features and guarantees that it gives that you don't find in this combination in other stream systems, which altogether make it actually applicable, nicely applicable to a wide variety of good use cases. So the first one is the core runtime of Flink as a streaming runtime is an entirely pipelined runtime. So we actually have a mode to do also batch exchanges in terms of fully buffered streams, but it is, if you use it in streaming, it's parameterized to be completely pipelined, end-to-end pipeline shuffles. The way that these pipelines run is that they also naturally flow control themselves. So if you have a task here that is very easy, and you have downstream tasks that are very heavy, the downstream tasks naturally back pressure the upstream tasks and apply flow control, so that they don't run out of sync. This is something that that gives you naturally the ingredients for low latency processing. The second part that we added to Flink is a very flexible handling of operator state. So if we're doing something on streaming data that is more than just taking the data stream, looking at every record individually, maybe parsing, replacing some values, filtering something, and then we're loading it into a search index or so, or we're inserting it into a database. If we're doing anything that looks at multiple records at a time, if we want to detect patterns, if we want to aggregate over windows, then the system is going to maintain some sort of state. The most generic and flexible variant of maintaining state in computation is actually maintaining user-defined state. One thing that is very important to notice, I think. Let me go back one slide. If you have a processor that is not based on mini batches and is running in a pipeline fashion, the individual operators are actually very long-lived. They're scheduled, they're started, and unless a failure happens, they actually stay around, right? They're not scheduled and torn down at the interval of every mini batch. So it is fairly easy to implement stateful computation just by maintaining some objects in your user function. People have been doing this in Storm a lot. Now, the interesting thing that we added to Flink is that this user-defined state, it hooks actually in the system's snapshot algorithm and the checkpointing method that we added, and the system gives you actually exactly once guarantees in which way data is reflected in these user-defined data structures that you create there. So the guarantees extend not just to any system-managed states, but as soon as you implement an interface in your user-defined function, they also extend to any state you keep around in your user function. That makes implementing a lot of complex logic very easy and still gives you very good guarantees. As that actually the state that you get when you operate on Windows, that you collect a certain amount of records, be that a slice of time of the stream, a count of records, be that a session window where you say, let me accumulate everything until I don't receive something for this particular group for a number of minutes, is in some sense just a special case of this state that the system transparently knows about. So if you solve actually this very generic form of state very well, then you get this very easily. Okay. fault tolerance for these stateful computations. How do we actually do that, or what do we do there in particular? So I think there are currently two forms of guarantees that different systems gives. The first one is what people like to call at least once processing. It is, for example, what Storm gives you as a guarantee, and that means in case something fails, it guarantees you it replays everything that you have lost, but because it doesn't know exactly how much you have lost, it may replay a little more. So you may have duplicates reflected in your state that you maintain, right? In contrast to that, exactly once is the guarantee that says, okay, I have a good notion of what has been lost, and I can replay exactly what I have lost. And in that way, I can guarantee that everything is reflected exactly once in my state. The last one is obviously much more interesting than the first one. The first one is easier to do. It just means you have to have a notion of being able to replay data, and if you're not sure how much to replay a little more, right? The last one is harder to do. The last one is where there I would say three coarse-grained approaches to do that. The first one is discretized streams or mini batches. We should actually add Trident here as well. It just says sparse streaming, but I think Trident should actually be mentioned there as well. Which means that you treat streaming as a series of atomic computations. A mini batch, once it's completed, everything has been reflected exactly once. If the mini batch fails, if one operator fails, I mean, the whole operator is lost. You just bring it up again, you start with a fresh state, and you apply everything naturally only once. So that is a very fast way to get this fault tolerance, but it comes with the drawbacks of having to cut the stream into mini batches, and something that is actually very interesting about this, that is maybe not obvious on first sight. This mini batch interval is naturally also the length of recovery. If you want to actually tune this in order to trade off recovery time and checkpointing overhead, you actually start changing the semantics of the program because it changes the window sizes, right? What Google Cloud Dataflow tries to do to get around this is not discretize the streams, but do more fine-grained operations as basically atomic transactions. This works very well if you have Google's infrastructure and have Spanner and Bigtable and so on, and you can just pump this. If you don't have this is a bit trickier, I would say, to realize, especially if especially if you don't have the Google infrastructure. So the third variant that we came up with for Flink is a variant of the Chandy-Lamport algorithm for drawing distributed snapshots of the state, and let me tell you really quickly what this looks like. So let's assume this is our streaming job, right? The green bubbles here are operators in Flink. They may be stateless, they may be stateful. Let's say the yellow tubes here are Kafka partitions. Let's make the assumption of Flink cooperating with Kafka here. Okay, so 4 parallel Kafka partitions and a set of Flink operators that consume from here. So at any point in time when the system decides to draw a checkpoint, and this may be actually fairly frequent, maybe every second, every half second or so, the job manager will send messages to the sources, to the adapters in Kafka, and what they do is they start injecting a logical barrier into the stream. This acts like a marker in the stream what part of the input is actually reflected in the checkpoint and what part is not reflected in the checkpoint. At the point of inserting these barriers in the stream, they will actually write their Kafka offsets or whatever offsets this is in the stream back to the job manager and forward these barriers into the stream. So these barriers start flowing through the stream, and they push records before them. So they trigger buffers, they trigger window computations and everything, and make sure that for example, when they reach an operator and they trigger checkpointing there, they make sure that before the checkpoint is triggered, all the records before the barrier are actually inserted into the operator state. And at the time of the barrier flowing through the operator, a copy of the operator state is drawn. This state is then sent to wherever you want to actually back it up. Like in the simplest most case, it's just sent to the master, or it can be sent to a distributed file system or some other replicated memory store. This can happen synchronously or asynchronously, depending on what this backend supports. And then the barriers flow through. The operators here basically sync on barrier arrival, what to reflect in the state and what not, and forward it. And once all barriers have reached all sinks, then you've actually drawn a snapshot. So this mechanism has a few very nice benefits. I think the foremost one is actually that the snapshotting doesn't interrupt the data flow. So it's a bit like doing these fine intervals like in mini batches, but they're actually flowing, they're overlaying. So you can have multiple of these things in progress at the same time. It's very easy if you have a longer topology that there are 5 checkpoint barriers, or 5 barriers from different checkpoints flowing after another. They're just triggering individually certain versions of the job to be committed, and then at some point a checkpoint is acknowledged and regarded as committed, and there are 5 others already in the background in process. So you can have a very fast interval that doesn't block any of the stream. And the other nice thing is because it doesn't bring up teardown operators. It doesn't really have to align with the intervals of the windows. You can tune sizes of windows and aggregation, granularities, and checkpointing interval completely independent of each other. So trading these things off, independent. And with this comes actually the ability to support extremely rich window semantics. So the windowing in Flink is actually something that is extremely nice, that a lot of people have started to like a lot. You can do more than time windows. You can do count windows, delta windows, session windows, and so on. We're labeling the windowing still as beta because we're trying to get an orthogonal set of windows where the semantics complement each other. Right now, it's a bit like we tried everything that we can do. Actually, we're trying to, bringing it to a more orthogonal set. So this may actually change in the future, but it's an extremely powerful windowing mechanism. And as such as it sort of gives you what I called initially a bit of a sweet spot combination of different features. You have a very high flexibility when it comes to windowing, when it comes to state. You don't have the problem that the checkpointing and windowing and aggregation granularities are sort of interdependent. You get the low latency, and checkpointing doesn't block anything. So that is so much for Flink's checkpointing. This is probably the only slide where I show a little bit of the APIs. It's word count again. Sorry for that, but at least it's 2 variants of it: the batch word count and the streaming word count. And I think the point that this slide here tries to make is, if you look at the 2 APIs, they're extremely similar. The only real difference is that this one here calls the basic data abstraction a data stream, while the other one calls it a data set. And on data streams, if you want to do anything that is grouping data, you basically have to define windows in which these groups are computed. And the batch API has, you can think of it implicitly, one global window that includes everything. So that's the main difference. Just a few words on the roadmap. We're working heavily on streaming. As I said, we're trying to also rework the windowing and their semantics a little bit. And the next big goal is to graduate this DataStream API from the beta status. And the other thing that we're working heavily on is actually providing more backends that you can put the state of your computation in, and actually exposing this. It's more like an internal API right now, but also exposing this to the programmer in the way that they can, for example, store the entire contents of Windows or the contents of their user-defined state, not inside Flink operations, but in outside operations. And that checkpointing sort of acts as group commits to the outside world and says, okay, whenever I'm drawing a snapshot, I'm coordinating with the outside world what is supposed to be regarded as consistently reflected and what might be rolled back as part of a recovery, and yeah, basically do interaction with versioning with the outside world there. There's actually work on getting the table API, which I explained as being a bit like Microsoft Link, for the dataset, also on top of DataStreams. The first version of that exists, but it doesn't support anything that requires windowing right now, so it's a bit limited. We're trying to add these windowing operations to the table API as well. And the interesting thing is, because this is very close to SQL, just that it's not a string in which you represent the query, but like a DSL program. This is like a good underpinning to actually add something like a SQL parser on top of it, right? The more longer-term goals that we're working on is Flink's master is currently not highly available, which is something that is highly desirable. So we've started working on that. In the space of like long-running queries, dynamic scale in and scale out is pretty important for reacting to load peaks. And the way we want to go about this is actually making scale in and scale out basically a controlled failure that comes with a checkpoint and a recovery with different parallelism. And there's actually work in progress to adapt the state interfaces such that this is that they actually understand the partitioning of the state and can redistribute state upon scale in and scale out. And yeah, then the libraries. Given that we're worrying a lot about data streaming right now, it's a natural next step for both the machine learning library and the graph library to actually add streaming variants of the algorithms. They currently only contain batch variants of the algorithms. Okay, do you actually want to see some code, or should I go on with slides? Code is good? Okay, then keep your fingers crossed that this actually is not what's it called in English? The demo effect or so, that whenever you try to demo something, it horribly fails. Okay. Let's see if I can do this. Okay, so.
What river is this one?
Say again?
What river is this?
It's a lake in Argentina. Okay. Let me actually briefly explain with the help of this slide here. Where's the cursor here? What this demo is showing. And I tried to pick a simple but I hope sort of interesting use case, and that is detecting event patterns using state machines. So what this scenario is motivated by is a simple thought experiment or use case to do, let's say, intrusion detection in networks, or just validating that certain actions happen in certain orders. So assume we have a set of machines here that generates events, maybe firewalls or authentication services that generate for certain users or IP addresses events when they come there. And these events are supposed to occur in certain orders. For example, there shouldn't be an interaction with some application server before some authentication has happened or so, right? So the events should follow a certain pattern, and if at any point in time you detect that this pattern is violated, then there's something goofy, right? And this should generate an alert. So what we have here is as a source a set of Kafka partitions which get the events from the different sources. The yellow bubbles are the Flink operations, a connector to Kafka which deserializes the events. It routes them based on, let's say, originating user or IP address. It's highly simplified, so bear with me here. And these are the interesting operations. They actually run a state machine, and they start at a certain state when they first receive an event. They transition to the next states, and they make sure that the next event actually does a valid transition. If not, then they generate an alert. And the sinks here, in our case, they just print the alerts to the command line. You can think of the sending messages to whatever dashboard you want to have these alerts displayed in. Okay, so the topology all in all is actually, I hope sufficiently simple for a demo. It's three operations: source, partition, state machine, and sink. Okay, I've implemented this in Can you actually see this? Probably not, no? Then let me switch the screen to mirrored. Okay. Okay, wow, this is a tough resolution. Okay, so what we have here is let's say the skeleton of the simplest skeleton of a Flink job, right? We have our enclosing Scala object. We have the main method. We start by creating a stream execution environment. We use this call here, get execution environment, that gives you the context defined environment. So if I run it from the IDE, it will give me an environment that spawns a local cluster in the background to allow me to debug the job. And because I'm running this in a VM that's not very powerful, I'm setting it to a parallelism of 4. And I'm creating a data stream here as adding a source to the environment, which is the event generator source. So the event generator source, let me quickly go into that one, doesn't actually look extremely complicated. These are the interesting parts. It just instantiates this generator, and then while running, collects generator next. This is an interval in which the IP addresses that the events are attached to should be generated. So it's a fairly simple example, albeit in. If we have time left later, I can switch to connecting this to Kafka. This is also fairly straightforward, but let's try this one first. Okay. Now that we have this sample stream, we can do a few things with it. So let's say the first thing that we do is actually print it, so you have an idea of what's going on here. So this defines the program. In the end, we have to tell the system to actually run this program, because it doesn't immediately trigger it as soon as you define the program. So let me hope that this resolution actually can show these things and that I didn't mess up my program, so it actually compiles. Okay, so yeah, that's what it looks like. It's just taking this stream and printing it. It prefixes it with let's say with a parallel instance that is doing this. So it's events, source IP address, and some form of interaction. Just label them A, B, C, D, E. You can think about it, firewall, authentication service, whatever. Okay, now if we want to do something interesting with that, the first thing we should make sure is that all events that correspond to the same source actually go to the same target. So we just, let's say, hash partition it, and what do we hash partition it on? So the types that are flowing through the system are these case classes here. Case class event, it has a source IP address. I was lazy, I just used an integer. It's IPv4, it's pretty outdated, but it's just for the sake of example, and an event type. And yeah, that's basically it. So what we want to root it on is the source address. So that's what we're going to tell the system. Okay, so. All right, so what happens here is you can just give it the name of the IP address. The system will analyze the program before you submit it, and it will actually generate a way of serializing this case class basically as a two-tuple, because it has two fields. As a Scala product type, and it will compile this down to a reference to a certain field in the tuple to a certain offset. So this is actually not using at runtime reflection and so on to look this up. Okay, so now that we've routed the events, we want to run them through the state machine. I've implemented the state machine as a flat map function. So the flat map function is actually just here. It's very simple. I have some state. Okay, I chose not to use a window because I want to have this very fine-grained control of the data structure here. So I'm just defining the state as a hash table, and whenever I'm receiving an event, here's the collector for alerts where I may want to push my alert to. The first thing I do is I take the current state that is associated with the event sequence from the source address. If I'm not getting anything, I assume it's the initial state I haven't seen this before. And then I tell the state machine, okay, transition with that event. If it is an invalid transition, collect an alert. Otherwise, if you transitioned and it's not a terminal state, then remember that. Does that make sense so far? Okay. So, we just flat map by this here. What did I call it? State machine mapper. Okay, I think I told my event generator to generate an illegal state transition once every 10 million events. So if we run this now, we should see some alerts and not the original events in the output. So again, it's bringing up the can I maximize this? Probably not. Huh? It's bringing up the system in the background, and you see the alert. So it's generating quite a few alerts here, even though it's doing an illegal transition once every 10,000 elements. So let's actually have a quick look what the throughput rate is for this. This is not just running. That is not just running passing a few elements through some list. What's actually happening is this is bringing up in the background a full Flink stack, including a network layer to route it. Serialization stack, it's putting it into buffers, it's flushing these buffers to the channels, it has latency watchdogs that say if events don't arrive in the necessary frequency to guarantee the latency, I'm early flushing the buffers and so on. So this is all happening here. So it's it gives you a good approximation of what the throughput is you can expect if you have let's say a decent network, right? If there's any bottleneck in Flink's mechanism to process these records, this would show in this setting. So I think in this events generator source, I added some code to actually give us the throughput that we get for this simple job here. That's including deserialization, hash partitioning, and running the state machine. So yeah, once this is actually ramped up, what we see here is that the throughput is roughly, let me stop it at some value. We're seeing this at all 4 parallel partitions that we see, and we see actually each parallel partition is processing something like 1.4 million per second or so. That is, including source generation, partitioning, shipping, and so on. That's per core on a VM. So I think it's actually a good number if you put this on serious machines. You can expect this to go up. Okay, so this is running without any guarantees right now. So how does it actually impact it if we start doing some state backup and so on? So one thing that we need to tell the system is how to actually salvage the state from this function in order to be able to restore it. So we just add the interface here with checkpointed. I can't type here, really, sorry. So, and what we're checkpointing is it's basically this hash table. This is what we want the system to save for us. In the simplest, most version, it's just applying Java serialization when it ships this to the persistent store. And yeah, of course now I have to implement a few methods. They're very simple in my case because I don't want to do a terrible lot of complicated stuff. I really just want to tell the system, take this exactly as it is and backup it. So this method here, snapshot state, is invoked by the system whenever it draws a snapshot. It gives you the ID of the checkpoint and a timestamp. These are not actually named nicely, these parameters. I don't seem to have the source code connected, but for our case here, they're actually not very important. They're important if you want to in some way interact with the outside world. If you want to restore state, we're getting the state that we should restore, and all we do is basically, when we restore it, our initial states should be empty, so we just add them back to our initial states. So that should be it. That tells the system, okay, here, this one should participate in the Gen-D Lamport snapshotting, and let's now tell the system to draw us a checkpoint every yeah, let's start with 1,000 milliseconds. Okay, let's see what happens. Okay, so it's, yeah. You're seeing the output from the checkpoint coordinate. Yeah, you can't read this. Okay, sorry. Okay, yeah, here. I don't know how to do this in IntelliJ. That I probably have to stop it for a second just to be able to scroll. Yeah. So what you basically see is you see triggering checkpoint and completed checkpoints when the barriers travel through. So it doesn't really take a long time for these checkpoints, like 30 milliseconds in the background. They're also not backing up a lot of state. I think the number of state machines that this generator keeps concurrently running boils down to, I think, maybe a megabyte or so per task. So it's not a terrible lot here that has to be snapshotted. But I mean, you can see the idea of the flow not being interrupted, but being able to continue at the same time, and the stream to keep running. The TCP connections, which have ramped up, just keep pushing, and everything else happens asynchronously in the background. If you look at these numbers again, they're actually pretty much like they used to be before, right? There hasn't really been much of a drop by doing a checkpoint every second. So let's see if we can get this down a little bit. And can we torture the system a bit and say, okay, it's snapshot every 400 milliseconds. I've not tried this before, so let's see what happens. I'm also on a development branch. This is extra exciting because any non-released experimental stuff here. Yeah. So what you actually see here, let me again stop this. You'll probably start to see overlapping checkpoints, or not even yet. No. So if we have more complex topologies, we'll start overlapping checkpoints, like triggering checkpoints 16, 17, 18, 19, and then 16 gets acknowledged and later and so on. So if you build more complex topologies, you can start seeing this behavior. Okay, do you want to see how to connect this to Kafka, or should we go on with the talk? What's your preference?
Kafka.
Okay. So one person said Kafka, so if nobody else objects, then let's do that. Okay, so in order to do this in Kafka, what we do is we basically just generate this stream in a different fashion. So instead of generating this sample stream here, we generate a stream using the Kafka source. So I'm running a Kafka mini cluster here on my machine against the temp directory that is, yeah. Don't expect a gigantic throughput from Kafka on this machine here. It's just not the right setup. Okay, I'm just saying this because Kafka can actually do much better than I can show this here. Okay, yeah. So it's basically the way you use Kafka. You configure some. You configure some properties. The important thing is that if we want to use the Flink's persistent Kafka source, which aligns the barriers in the Kafka stream together with the snapshots, then we have to make sure that Kafka doesn't auto-commit because we commit at the end of a snapshot. So that we're reading and we're keeping the offsets uncommitted until we reach the end of a snapshot, and then we commit them back into Zookeeper. So it's a bit like batch commit into group commit into Zookeeper. So yeah, I'm giving it the IP address and the group and the demo topic, and here's just the deserializer for the event data type, which tells you how to turn the bytes into this event type, and the consumer config is Kafka's wrap around this. So let's oh, sorry, I think I confused the lines here. Okay, so if we do this on the Kafka stream here, then we shouldn't see anything initially because we're not putting anything in Kafka. Or maybe there's just from the last generator I ran, there may be some residual data. Yeah, there's probably some residual data in here, yeah, that caused the first invalid state transitions. We're also still checkpointing at 400 milliseconds, so let's not do that, because otherwise we're not going to see anything in the command line but these messages here. Let me set this to something like a second or 2 seconds so it doesn't flood the command line. The overhead of checkpointing with Kafka is basically not different than checkpointing locally, because all it really does is it treats the offsets in Kafka as some user-defined state that becomes part of the snapshot. Okay, good. Let me start this again and then start another program that puts some data into Kafka. Okay, so we're seeing some stuff that it picked up from Kafka that used to be there and didn't align with any prior state, and then the messages from the checkpoint coordinator. Okay, I have another program here that generates data into Kafka. Okay, so by default it generates the data basically with a proper state machine, and it's not causing any illegal state transition. So as soon as I hit this here, it will generate an illegal state transition, and yeah, okay, we see the alert over there. So I have no idea how to put these windows next to each other in IntelliJ. Otherwise, I think you can see that by the time you actually hit the button to generate the illegal state transition, I think the other side already reflects it. So the latency is actually pretty sweet here. Yep. Okay, so much for how much I can do with Kafka on this mini cluster. So connecting to Kafka here is it's basically these 4 lines of code, and this also, since if we chose the persistent Kafka source here, this makes this automatically participate in the snapshotting as soon as we enable the checkpointing here. So I think it's pretty lightweight integration. Okay, do I have a few more minutes for some slides, or are we over time already?
2 minutes.
2 minutes, okay. Then let me just get maybe 2 messages really quick across, and that is the following. So I said initially that Flink is a stream processor that exposes itself as well as a batch processor, and the way it does it is it treats batch programs as a special kind of streaming program. So where a streaming program is a program over an infinite stream, a batch program is a program over a finite stream. This is actually not a very far-fetched idea if you think about it, right? Anything for example, in Hadoop, when you consume a file, you're not loading the file entirely in memory, you're consuming a file stream, right? And you're reading it bit by bit, and the mapper is producing it bit by bit. And if you wish, doing batch as streaming means just thinking this all the way through. The shuffle also is, I mean, it's not element by elements, buffer by buffer, but it's along the same lines. The reducers can, if they are like running hash reducers, they can start doing this work already, and so on. In streaming, if you want to do any grouped operations, you cannot wait for the entire stream to be consumed because it's infinite, so you do windows. And in batch, you implicitly have a window that is the entire stream, right? So the window is full and triggers as soon as you reach the end of the stream. And where streaming programs do pipeline data exchange always, the batch programs do pipeline data exchange or blocking data exchange. Actually, most of the time you run them in Flink, they do pipeline data exchange. Blocking is to resolve deadlocks and to break the program into finer schedulable units. So with that, let me actually skip over all these other slides. There are a few neat other things in Flink that we'll have to go to the Flink meetup tomorrow if you want to hear more about them. Like closed loop iterations, feedback in the data flow that gives actually pretty good performance also for batch machine learning, and also enables online machine learning. Stateful iterations, which make use of the fact that you can keep state around. You don't recompute a model the entire time, but you can keep updating whatever changed and build recomputation based on changes instead of like recomputing or at least forwarding all data every time. And like I said before, on the batch side, there are code paths that do static code analysis, optimization of these programs. Quite some interesting stuff. So I think Alexei said initially that the Flink sort of popped out of nowhere all of a sudden. If you look at the timeline here, it's not quite true. It has been doing quite a bit of work. It has not been as heavily advertised. It basically started, let's say, a year ago when we went to Apache. Before that, it was a project that was a not too small community, but a community was a bit close in itself. So, but now it's actually it's gaining quite a few contributors. And yeah, if you find this exciting, follow us either on Twitter, subscribe to the news mailing list, or read the Flink blog once in a while. It has actually some interesting technical pieces. And if you actually want to learn even more, then we're organizing the first conference on Flink in Berlin in October. It's called Flink Forward. I think the call for submissions is actually still open, right? So if you're trying it out, or just interested in talking about other related things, or just about ideas, send us a submission. And if you want to learn about the other interesting parts that I couldn't really talk about today, then come tomorrow to the Flink Bay Area meetup. I don't remember the exact address, but yeah, I mean, you'll find it. It's a meetup group. Yeah, okay, with that, I'm done. Thank you.
So guys, we're really over time, but we'll just take one question, and maybe then you can ask folks offline. And come tomorrow to the meetup. Yeah.
Mm-hmm.
Yeah.
Using the high-level consumer or the low-level consumer for Kafka integration?
Okay, say that again.
Are you using the low-level or the high-level consumer for the Kafka integration?
Okay. We are using, Robert, you can correct me if I'm wrong. I think we originally used the low-level consumer, but it was pretty hard because all the broker failures and master re-elections were up to us, and then we switched to the high-level consumers, but we overrode the committing behavior of the high-level consumer. I think this is what we do. So it's a modified high-level consumer, I think. Okay, Robert nods. That means I've said it correctly. Okay. Do we have time for a second question?
Just do it. Don't ask.
What does Flink mean in German?
Oh, Flink means swift or agile or nimble in German. Yeah, actually it means it also in Swedish, and we've since learned that it means brave in Dutch, so it means a lot of good things in different languages that we had no idea about. All right, thank you.